Okay, here we're going to review some of the key concepts about electric circuits. In particular, we're going to review the concepts of voltage, current, and resistance, which then leads us to Ohm's law, that current is voltage divided by resistance. First term we're going to look at is voltage. Although we're going to be actually using power supplies that we plug into an outlet, it's probably a little bit easier to see voltage in terms of a battery. Inside a battery, we have an oxidation-reduction reaction going on. There are two reagents. One of them is called the oxidizer. It gains electrons. The other is called the reducer. It loses electrons. And it is this exchange of electrons that actually produces the voltage that's generated in the battery. What really happens effectively is that one of the elements will have an electron in an orbital that is actually fairly far from the nucleus. It wants to get as close to a nucleus as it possibly can because the electron is negatively charged. The nucleus is obviously positively charged. If it goes to another atom, which is the nucleus of the oxidizer, it'll be in an orbital that is a little bit closer to the nucleus. It will therefore lose energy, and that loss in energy is what produces the energy that is used in a circuit, or the voltage of the battery. Another way to describe the exact same thing is that the chemical reaction effectively is doing work to separate charge, to take charge away from one atom and put them on another atom. That work is what produces a voltage. Now, a voltage is actually not directly work, it is actually work per unit charge. Or if we say something has a 1.5 volts, which is a typical voltage for a battery, it says that 1 coulomb of electrons produced by the flowing out of the battery will gain 1.5 joules of energy, because a volt, the unit for voltage, is defined as basically the average energy or the average work done per unit charge. So 1 volt is 1 joule per coulomb of charge. Voltage, because it's an abstract concept, we often describe it in terms of analogies, and here I have two of them. One is a slide where electric potential energy is essentially replaced by gravitational potential energy. So at one end of the slide, we have high gravitational potential energy. The other end of the slide, we have low potential energy. What matters in a circuit is not the voltage that we have, but rather the differences in voltage from one end of a wire to the other end of a wire. Those changes are what produce an electric field or a force that pushes charges through a circuit. A force, as we will see, is actually caused by the rate of change in potential energy, or the derivative of potential energy. And the slope, which is the derivative, is determined by this incline right here, the incline of the slide. So the incline plays an analogous role in gravity that a voltage plays in circuits, because that is what produces the electric field that causes the current to flow. The second analogy is using pressure, because the only thing that matters is differences in pressure. When we have water, for an example, flowing through this tube, we have one at high pressure and the other end at low pressure. That will cause water to flow through the tube. If the pressure on either end of the tube is the same, even if it's high pressure at both sides, then nothing will cause the water to flow. We will not have any current flowing. So this pressure plays a role that's somewhat analogous to voltage. If this is at high voltage and that is at low voltage, then we'll have current flowing through a wire, just like high pressure and low pressure will cause a fluid to flow. Now, when it comes to current, or the flow of charge, if we're talking first about a conductor, conductors have what are called the so-called sea of electrons. These are the electrons that actually flow in a wire. The important part is that they move randomly at very high speeds, on the order of 10 to the 5th meters per second. But they're moving in all directions randomly, not producing any net flow from one side to the other of a wire, because for every electron that's flowing from left to right, you'll have one flowing the opposite direction, no net charge flowing. If we take a battery, what the battery is going to produce is an external electric field, which will apply a force to the electrons and cause them to begin to slowly drift in the direction of the force. And that continuous flow will actually be the current. However, that current will result in a very slow drift speed of on the order of a fraction of a millimeter per second. So what we're actually having here is electrons moving randomly in all directions while slowly drifting in the direction of the electric field at incredibly slow speeds. The unit we use for electric current is called an ampere, or an amp for short. An amp is defined as 1 coulomb of charge flowing per second, where a coulomb is 6.25 times 10 to the 18th electrons, and a 1 amp current is that number of electrons flowing through a circuit every second. Now, I mentioned that was for a conductor. There are 3 general types of materials: insulators, semiconductors, and conductors. And one important point is that everything can conduct. We call something an insulator not because it can't conduct, but rather because it's very hard to get it to conduct. Diagram right here shows basically the energy levels for an insulator. These energy levels are kind of like the energy levels you've seen for atoms like hydrogen and helium. And notice this is the equivalent of like having the 1s orbital and the 2s orbital. Electrons can be in one orbital or the next orbital. They cannot be in between. Likewise, in a solid, we can have electrons in this band right here, which is called the valence band. That is where they're in covalent bonds. Or they can be in this largely empty conduction band, which has many empty states, so the electrons can readily move within this conduction band. However, in an insulator, there's a very large gap between those two. This is filled with electrons. This one is empty. If you were to get an electron out of the valence band and into the conduction band, it can conduct electricity. Difference in an insulator is this gap is so large you would need many, many volts in order to get electrons to jump from here to there. Once that happens, then the insulator will become a conductor. It's just that's very hard. Semiconductors are similar to insulators, except the band gap is very small. And just by heating them up to room temperature even, some of these electrons will gain enough random thermal energy to jump into the conduction band where they can in fact conduct. In addition, if I apply a voltage, I can also knock electrons into the conduction band and they will begin to move. And again, the semiconductor will conduct. So this is effectively a cross between an insulator, which doesn't conduct well at all because the gap is very big, and a conductor where the two bands actually overlap. So the valence band overlaps with the conduction band, which means all of the electrons in the valence band readily can jump into the conduction band because there's no gap in between them. That's why we call this the sea of electrons, because all of the electrons in the valence band can easily move into the conduction band. There's no gap between them. It's kind of like the 1s and the 2s orbitals basically being so close to each other that all you need is to add a very little bit of energy, and you can jump from one energy state to the other. And that's what a conductor is. It simply is a metal or material that has the two bands overlapping. So as a result, the electrons can very easily move around. Now, the next concept is resistance, and this applies specifically to conductors. Namely, given what I just described, is you would think, well, why doesn't everything flow very readily? Well, what limits the flow is the thickness of the wire. Because if you have a very thin wire, what you're trying to do is take lots of electrons and get them to go in a very narrow region. The electrons don't want to be near each other. So that will restrict it. If, on the other hand, you have a very, very thick wire, then the electrons can spread apart as they flow through the wire, and they will conduct better. The length of the wire also determines how well the current can flow in it. Because remember, the electric force is basically due to a potential difference across the wire, and it's really the slope, and that's rise over run. The rise is the potential difference. The run is the length of the wire. The longer the wire, the smaller the slope, and therefore the weaker the force and the less current you're going to get to conduct. The conduction will also depend on the composition of the wire, which we call the resistivity. For an example, copper conducts electricity a little bit better than aluminum does. It has a slightly lower resistivity. Also, the temperature of the wire will affect the conductivity. If I have a conductor and I heat it up, the atoms will be jostling around a lot, and as they jostle around a lot, it will be harder for the electrons, in effect, to make their way through this jostling of atoms, and that will reduce the conductivity or increase the resistance. And that is determined by this symbol alpha, which is the thermal coefficient. Now, the unit we use for resistance is called the ohm, and we use the Greek letter omega for a symbol of it. An ohm is simply how many volts does it take to produce a standard current of 1 amp. So a 1 ohm resistor means it takes literally 1 volt to produce a 1 amp current. If I have a wire that has a resistance of 2 ohms, then it takes 2 volts to produce the same 1 amp current. A 1000 ohm resistor means it would require 1000 volts to produce that 1 amp of current. Now, all of these dependencies can be summarized in this equation, where the resistance is equal to the resistivity times the length of the wire divided by the cross-sectional area. And the temperature right here, the way we define the dependence, is T0 is the reference temperature, at which point, if I'm at that temperature, the resistance is this term right here. If I'm above that, then I get a higher resistance. If I'm below that, I get a lower resistance. So we use a reference temperature. Often that reference temperature is 20 degrees Celsius, or room temperature. So that gives us our key terms. Voltage, which basically is like a force. It is literally due to the difference in electric potential across a wire. And it is measured in volts, which is joules of QPE is electrical potential energy, because the letter Q is often used to describe electric charge, per coulomb. The current, which is the flow of electrons, is measured in amps, and that's 1 coulomb flowing per second. Notice it does not tell you how fast the electrons are going. It is rather how many electrons are flowing. And the resistance is basically determined by the wire. It's what restricts the flow of current. It's measured in an ohm, and an ohm is how many volts does it take to produce 1 amp. This then leads us to Ohm's law, which is how these three things are related. The current is equal to the potential difference across the wire divided by the resistance of the wire, which is often also written as voltage equals resistance times current. Notice it is important that the voltage here is actually the difference in electric potential. Often that is just written as I equals V over R. That V is a bit deceptive because it's not V per se, it's actually the difference in voltage across the wire. One last thing to remember is that our flow of current actually comes from Ben Franklin. Ben Franklin, turns out, erroneously believed that the charges that flowed actually were positive because he defined it in terms of glass. And he said glass gets charged as positive charge flowing onto glass. Largely, if you rub it with silk, he thought charges left the silk and went onto the glass. When you rubbed amber, the charges flowed off from it and onto the fur. Amber, therefore, was defined to be negative charges, and glass was defined to be positive charge. However, as it turns out, we now understand atomic structure a little bit better, it turns out that what's actually flowing is electrons off from amber, and that means electrons flowing onto amber, which actually means amber has a negative charge because it's gaining electrons, and glass has a positive charge because it is losing electrons. This then means that conventional current, which is based on Ben Franklin, is positive charges moving in one direction. In reality, we actually have the negatively charged electrons. This was not discovered until the 20th century. The convention had been set, and it was basically just decided to keep with the Ben Franklin convention of positive charges moving, even though it is actually electrons that are free to move. And that's just a historical happenstance. It does turn out that it doesn't really make any difference, so the convention has been established and has been kept.